dear guest of honor, dear rectorate, dear participants, also from my side, a very warm welcome. I'm going to show you in the next 10 minutes how Marvin is going to help us, hopefully, in chemistry. Usually chemistry is a very experimental science, but my field is computational chemistry, so I work a lot with the computer, and I want to find solutions, and I mean solutions in two ways. First of all, I mean solutions for underlying physical equations that we need to solve in order to calculate on Marvin, but I also mean solutions in the sense of chemistry. So mixtures of solutes, some compounds in liquids, and I'm going to show you on the next slide what our research is about. I mentioned already liquids, so we are studying liquids in my group, and one of the most famous liquid, which you are all drinking now, is water. And another liquid that we are studying is ionic liquids. We develop some methods and we develop software, so we interact very much with the computer. Studying liquids is also very special because it leads you immediately to very nice applications. For instance, in energy devices like solar cells, batteries, and supercapacitors, but also you can study carbon dioxide capture in them. You use them for extraction and recycling, and you see that they are very interesting applications. Now, imagine these applications are very complicated and very complex. But already the liquids are very complex, and if you want to study them, you have to have a lot of computer time, and I try to illustrate that with the example from everyday life, and I say this now in German, wie viele Haare ergeben eine Frisur? So you see here in the middle, some of my colleagues, and you see even the more bold ones up there, they have more than one hair. And it's, with studying liquids, it's similar. So here's one of our chiral molecules. You see it here, and when we want to study it in condensed phase, in the liquid situation, we don't get away with looking at only one water molecule. We need to have more than one of these. And on this side, you see a simulation box that we set up when we are going to calculate, and you see there's more than one water molecule in there, so size matters, and I hope I could convince you that size matters, but there's more to it. Imagine how far you can jump. So if you look at Malaika Mihambo, her record is 7.3 meters. Unfortunately, she is injured at the moment, but it's an enormous number. Now, if we look at this number, it's great and it's huge, but we don't know anything about her techniques. So if we want to learn from her how to jump, we need more information. And in order to illustrate this, I show you this movie. So averages hide this kind of information. Imagine diffusion or hydrogen bonding. Here you see a water molecule. The red one is the oxygen atom, and the white ones are hydrogen atoms, and they're polarized negatively and positively. So if you have a lot of them, they can form some interactions, which we call hydrogen bond, Wasserstoffbrücke, and you see that they are very dynamical. They come and go. So if you look at only averages, then you wouldn't see this dynamical behavior similar. If you look at diffusion, you don't know where does it come from. So a molecule also diffuses through a liquid. And so this starts here, then it goes maybe over there. And if you look only at an average or only at the spatial density, you don't know anything about that. So we need these trajectories to track the movement over time. And these are these movies, and they are very expensive to calculate. So you have to calculate each of these steps, and therefore we need computers like Marvin. Now, we want to go even further. Another example from everyday life, imagine if you go hiking. If you go hiking, you go climb mountains, and in order to be able to do that, you need to bring snacks and water in order to restore the energy what you use when you climb these mountains. Similarly, when you look at a reaction, and here I show you something special of water, which is responsible for the pH, and other phenomena. Here in the middle you see now a water molecule that has an additional proton, so it's positively charged. And you will see in the course of the reaction that indicated by the color that one proton jumps from from one molecule to the other. And you see that bonds are broken and formed, and this costs even more energy. And this also causes the need for new methods to describe that. So you see this, the proton is here in water very fast because it can change its identity by forming and breaking bonds. You saw we started here with the blue one, and now it transfers over to the brown or the violet water molecule. I want to show you another reaction, namely the carbon dioxide capture in ionic liquids. And so far I have not explained to you what ionic liquids are. And for this I brought you a movie from my co-worker, Wahide Alizadeh, which she produced when we had to give an online talk during Corona.
Hallo aus Homeoffice, mein Name ist Wahide Alizadeh. Ich bin Doktorandin im Arbeitsgruppe Frau Professor Kirchner. Wie wir es normalerweise kennen, ist das Salz fest. Es gibt die sogenannte ionische Flüssigkeit, was eigentlich auch Salz sind, aber im flüssigen Zustand. Professor Kirchner wird mir dazu erzählen. Einen schönen Tag noch.
So for those of you who didn't understand it, Wahide says that normally we know the salt as a solid, but ionic liquids are so special. They are also salts, but they are liquid. You can see in the movie that it's able to capture CO2. There's a CO2 molecule here, and you see it has to bend. Usually CO2 is linear. It has to bend to react with this anion, and if we want to understand this, we need again the help of Marvin. And if we understand this, we can suggest optimal liquids that can maybe even better capture the carbon dioxide. Okay, I showed you now the liquid in situations of carbon dioxide capture and in other situations, but liquids also play an enormous role in energy devices. I said that in the beginning. And here the everyday life example is, imagine if you have to queue here because you want to enter a building, and imagine you have to very fast transport some charge along this queue, because this is one of the duties or one of the things electrolyte should do. It should be able to carry charge very fast, but also it has to adjust to situations where the electrochemical reaction is taking part very positively. And a third thing, and this is what I'm going to show you in the movie, is that the electrolyte has to fit to situations where it has to interact with the electrode. So this carbon nanotube can function as an electrode, and the ionic liquid has to fit in here. And I show you now. If you look at the parts where you have a normal liquid that's randomly distributed or distributed how a liquid distributes, but if you look inside the carbon nanotube, you see that there's a ring-like structure, and that means the liquid behaves differently than outside here. And as you see, we had now a solid structure here and there, and this is even more expensive to calculate, but it's important to get knowledge about that. Now I brought you all the time an everyday life in order to illustrate what we are doing, but here I want to show you that computational chemistry can of course also interact with research where the human is part of the study. And this is research of my former postdoc, Professor Dr. Oldemir Holotsky, who is a pioneering expert in plastic simulations. And we all know plastic is a great material, but it's polluting the environment. And we have to know what is it doing in the environment. And in this study, this is very nice, Oldemir, and wanted to know what is plastic doing, nanoplastic doing in water, and what happens if we have another substance that does not belong in water, namely a drug, tetracycline here. And the simulation shows you the following. So this little brown red thing, that was the tetracycline. So it sometimes comes to the surface, but in the end you see the nanoplastic completely swallows it. And for those of you who remember Pac-Man, the computer game, you see there's quite a resemblance. Now you can say, so what? What do I care about this? But there's even more. Oldermoor studied together with physicians in Vienna the nanoplastic with a cholesterol corona at the blood-brain barrier. And you can see what happens in this movie. You see that it's very impressive. The nanoplastic can enter the membrane. So let's see that again. Again, you see this is a very complex calculation. You have lots of molecules, you have dynamics, you have lots of interfaces, and you see that the result is that this nanoplastic can go into this can go into the brain, and you can imagine this caused a lot of discussions in literature. So it was a very important study. But I showed this, especially this plastic example, also for one reason, namely most of these calculations were carried out in Bonn. So you see that Bonn also, so computers like Marvin also help to foster young researchers. So they need to have this computer time to be able to play with their ideas. And this brings me to the end of my talk, where I would like to thank, first of all, my group. You see here Valhide again. And Leonard did most of the movies. He simulated the carbon nanotube and also the nanoplastic. And you see that we try to mimic here a property of ionic liquids, namely microheterogeneity. So you see there's a separation of parts of the liquid, namely there are polar and non-polar parts, and they separate. And we try to model that somehow. I would also like to thank Petra Mutzel, because she is a great addition on many levels to the University of Bonn. It's just great to be in the environment of more women, I can tell that. And I would like to thank the Bonn supercomputer team, especially because they are very patient people, and we can use their computers, and they help us, and there's really a support, and this is great. And I would also like to thank the University of Bonn, because Bonn is a very special place. It's a very special place for doing science on a high level, and this is not at every place like this. And I would like to thank you for your attention.